Stanford University.
All right, we've really studied two different theories a little bit, quantum electrodynamics and quantum chromodynamics. Both of them are gauge theories. In fact, just about all of nature as we know it, in one way or another, is controlled by gauge theories of different kinds. And so I ought to tell you what a gauge theory is. Now, I'm not going to get into in any depth what gauge symmetry is. I'm going to tell you what a gauge theory is in more or less the minimal mathematical way. The first and simplest gauge theory is Maxwell's theory. Maxwell's theory of light, or Maxwell's theory of electromagnetism. Let's not worry about what the word gauge means. We may go through it later, but not now. But what it is a theory of fields which have all of the properties of the electromagnetic field. The electromagnetic field has 6 components, 3 components of electric field, 3 components of magnetic field. You can represent those 6 components in terms of a 4-vector called the vector potential. I'll just write it down for you. It's not going to play any big role today anyway, but just to tell you, there's a 4-vector that's generally called A, and it has an index mu. It has 4 components, a 0, that's the time component of it, and the 3 space components, A1, 2, and 3, or AX, Y, and Z. Let's not write them out in detail. So it contains a 3-vector and a 4th component, A0. The significance of A0 is that it's the electrostatic potential. It's the thing whose gradient is the electric force. Okay? So for example, the electric force on a charged particle is just gotten by multiplying the electric charge by the gradient or the derivative Fx, derivative of A0 with respect to x. So it's just the electrostatic potential. It's measured in volts, or in particle physics, of course, it's not measured in volts. Volts per unit charge, excuse me. Volts, yeah. It's measured in whatever way you measure electrostatic potential. That's the meaning of A0. All right. Notice, first of all, oh, and of course, this is the electric field. This is the electric field. It has 3 components, derivative with respect to x, y, or z. So it's the gradient of A. Right? And the gradient of A is just called the electric field. So the electric field is determined by the gradient of A0. And the magnetic field is determined by also derivatives of the vector potential. And in fact, the magnetic field is the curl of the vector potential. So one of 2 ways you can study electrodynamics, either in terms of the electric and magnetic fields, of which there are 6, or in terms of the vector potential, of which there are 4, but they're equivalent descriptions of electrodynamics, and we won't go into Maxwell's equations. But let me just remind you that Maxwell's equations give rise to electromagnetic waves. An electromagnetic wave is a wave of electric and magnetic field, and a typical electromagnetic wave has a direction in space that it moves. Let's just represent it by an arrow. And it has a polarization. To understand what the polarization means, you have to think about the electric and magnetic fields. And the electric and magnetic fields oscillate as you go down the wave. Here's the electric field, for example. The whole thing moves with the speed of light. But at any given instant, the electric field might look like that. And the magnetic field is always perpendicular to the electric field. Let's try to draw it, see if I can give a drawing. I'm imagining the electric field is in the horizontal plane, and it's always perpendicular to the, let's see, is this going to, it's always perpendicular, like so. In appropriate units, the electric and magnetic field are equal to each other and perpendicular. This would be a plane polarized electromagnetic wave. In a plane polarized electromagnetic wave, the direction of polarization, which of course is always perpendicular to the direction of motion, the direction of polarization is determined by the electric field. So the electric field determines the direction of polarization, and that's electromagnetism, and that's electromagnetic waves in a nutshell. The other thing, of course, about electromagnetic waves is that there are sources. The sources are charges and currents, but let's particularly focus on the sources of the electric field. The sources of the electric field are electric charge. And to just draw a picture, to put it at the level of pictures, every electric charge creates an electric field. The electric field lines never end except on other charges. A positive convention, the convention is a positive electric charge puts out an electric field which is radially outward, falls off as 1 over r squared. You can imagine that the number of electric field lines coming out of a charge is fixed, proportional to the charge, and therefore the number of electric field lines passing through any sphere is the same no matter how far the sphere is. To say that mathematically, the integral of the electric field over the sphere is the same wherever you go, however far out you go. That's Gauss's law. That's Gauss's law. And that Gauss's law has a very strong consequence. If you don't have any other charges in the system, let's say just a plus charge, then you can't get, and the rule is electric lines only end on charges, then there's no way to get rid of a charge. No way to get rid of a charge. If you try to get rid of the charge, either the electric field has to suddenly disappear everywheres. That would violate the rules of the speed of light, that you can't send a signal faster than the speed of light. So instead, if you said that a wave moved outward of missing electric field, that also wouldn't make sense, not unless there were charges at the endpoints of the electric field. So all this would really be is this would not be the elimination of the charge. It would just be taking the charge and sending it out as a shell. It would be a shell of charge going out. The charge would not have disappeared. So it's a consequence, a deep consequence of the structure, the mathematical structure, Gauss's law and other laws, that electric charge is conserved. That is the essence of a gauge theory. Essence of a gauge theory, Maxwell-like fields, I'll use the word Maxwell-like because they're not all truly Maxwell's electromagnetic field. Maxwell-like fields consisting of electric-like and magnetic-like fields. If the gauge field is weakly coupled, and I will tell you what that means later, but it basically means that if the interactions between the parts of the electromagnetic field are weak enough that they don't interact with each other seriously, then the motion of a gauge field is exactly the same as a light wave. It will have a polarization. It will move down the axis with the speed of light, unless something else, unless there's something in the dynamics that changes that, naively at least, it's in every way similar to the electromagnetic field. The only difference is it also has sources. Every gauge field has sources analogous to the electric charge, but it may not be the electric charge. It might be something else. Let me give you an example which is an unphysical example. Unphysical not because it's inconsistent, but because it just happens not to be true as far as we know. There is another quantity in nature called the baryon number. It's simply the number of quarks. but it's a conserved quantity. And you could imagine that baryon number is the source of, now baryon number is not electric charge. Why not? Well, because protons and neutrons have it, so it is not electric charge, but it could be the source of its own gauge field. If it were, that would mean that there would be forces between protons, neutrons, protons, protons, neutrons, neutrons, that would be analogous to the Coulomb forces between charges, except they would have nothing to do with electric charge. They would have only to do with baryon number. So, for example, two objects with the same baryon number would repel each other. A proton and a neutron would repel each other because they have the same baryon number. A proton and a proton would repel. On the other hand, proton and antiproton having opposite baryon number would attract. Now, the only rub in this ointment is that there is no such gauge field coupled to the baryon number. Baryon number does not come with a field like this that surrounds it and no long-range force associated with it. So baryon number is not an example. Color is an example. And the color forces of quantum chromodynamics also. Oh, well, before I do that, one or two other points. The other point, of course, is this is a completely classical description of an electromagnetic wave. The corresponding quantum mechanical description is in terms of quanta, but of course, if we think of quanta as particles, at least that's about the only mental picture that we have to describe these discrete little objects. The discrete little objects, which drawing them, of course, is always misleading, but let me draw a photon. There's a photon, a little point. That little photon has a position, moves with the speed of light, but also it has a little flag associated with it, and that little flag is its polarization. I won't try to draw a flag on it. In other words, it has a pointer which either points this way, or somewhere in between, that indicates the polarization of the electromagnetic wave, of which it is a quantum. That's a complicated statement, but I think you get it. So photons come with polarization, and that polarization in principle can be rotated. You can rotate it by sending it through a quarter wave plate or in any number of ways. And that's photons. That's the photon theory of electromagnetism. And in the quantum theory, one can think of the Coulomb field as, roughly speaking, a field set up by the emission and absorption of photons, emission and absorption of these photons. Okay, so that's electrodynamics in a nutshell. Electrons are charged, protons are charged, and so forth, and they interact in this way with the gauge field. Another aspect of gauge fields, I've already mentioned it, that there's always conservation laws associated with them, namely conservation of the sources. But conservation laws in both quantum mechanics and classical mechanics are always associated with symmetries. Symmetries of some sort or another are always behind conservation laws. The conservation of electric charge, we've talked about that, and I showed you how if you study the quantum mechanics of electrons in terms of charged particles in general, there's a wave field describing those particles. This could be the electron. And the symmetry associated with the conservation of charge is just the multiplication of the field by a phase. So that was the simplest example of a gauge theory, a gauge charge, meaning the electric charge, and a symmetry that goes along with the conservation of that charge. Those things go together. Okay, well, let me just very quickly remind you how it worked in quantum chromodynamics. In quantum chromodynamics, a more complicated structure You do have Maxwell-like fields. Let's label them. The Maxwell-like fields are labeled by indices. So in quantum, let's continue to call them A. There is no universal symbol for the gauge field of quantum chromodynamics. Sometimes it's called G, sometimes it's called A, sometimes it's called B, sometimes it's called C. I'm going to call it A, but in order to distinguish it from the electromagnetic field, we give it some indices, I and J. It's a matrix. Now, it's a matrix, and that matrix transforms under a group. The group was SU3. So let me just remind you very, very quickly that we started thinking about SU3 not by thinking about gluons, this of course would be the gluon field, but by thinking about quarks. Right? So a quark was an object which we called Q. Q could stand for the quantum field of the quark, and it has an index. The index, it's not the up-down index, it's not the charm-strange index, we'll come to that sooner or later. It is the color index, red, green, or blue. I takes on 3 values. And the symmetry operation is not multiplying by e to the I theta, but multiplying by a unitary, special unitary matrix, Uij, gives us Q prime I. That was the symmetry operation, which is a kind of rotation in a kind of 3-dimensional complex space. Don't confuse it with ordinary 3-dimensional space. This was the symmetry operation. And one would say that the Q's, think of them as particles if you like, the Q's form a representation of SU3 which is called the fundamental representation. It's called the fundamental representation. It has 3 entries, red, green, and blue. Sometimes it's called the defining representation. It's the smallest non-trivial representation. And it just can be thought of as a 3-component vector, 1, 2, 3. And the unitary matrices can be thought of as matrices, 3 by 3 matrices. Okay, we've gone through that. The other thing that I told you is that antiquarks, or antiparticles in general, are represented by the complex conjugate fields, fields which are simply the complex conjugates of the original ones. The relation, the mathematical relation between particle and antiparticle, or the wave functions of particles and antiparticles, that relationship is complex conjugation. So we could ask, how do antiparticles transform? Well, we simply realize that if you want to transform the complex conjugate field, you should use the complex conjugate matrix. If you multiply Q by U to get Q prime, then you must multiply Q star by U star to get Q prime star. The set of matrices U are called a representation of the group. The set of matrices U star are a distinct and different representation of the group, and the language one would use is that quarks and antiquarks are described by the three-dimensional representation, and we could call it 3 star, meaning complex conjugate. It's usually indicated by a bar. 2 different representations of SU3. Right.
So there's 7 U matrices?
How many?
7? You said 7.
8. 9, actually. Well, sorry. You asked me how many matrices there are?
For U, I guess that's the number of generators.
The number of generators is 8. Yeah, because these matrices are assumed to be special unitary matrices. Now you can ask, and it's interesting to ask, what kind of theory would you make if you didn't insist that they be special? and I'll tell you another time, or maybe later, but not now. Okay, now what is Aij? Aij has two indices, and the way to think about it is that one of those, it is mathematically got the same group theory structure, the same symmetry structure as having a quark J and an anti-quark I. In other words, this is an object whose indices transform one index as the three-dimensional representation and the other index as the three-bar. Another way to think about it is it has all of the properties with respect to the symmetry, not with respect to all physical properties, but with respect to the way it transforms as if it were a quark and an anti-quark sitting on top of each other. Not its spin, just its color, as if it were a quark and an anti-quark, with one special rule, namely the trace of Aij vanishes. The singlet that you can make, the piece which has no transformation property under the group at all, that you can kill and forget about. That's why there are 8 Aij's instead of 9. So Aij is like a thing with a quark and an anti-quark index. But because it has a quark and an anti-quark index, it also transforms when you under the SU3 transformation group. In that sense, it's different than the photon. The photon is completely electrically neutral. Its field, the photon field, does not get a phase when you rotate the electron wave function. Electrons go to e to the I theta times electrons. Positrons go to e to the minus I theta times positrons. Photons do nothing. That's because they don't have electric charge. But the gluons, they do have color. Now, what kind of color do they have? They have the color of a particle and an antiparticle. And you say, well, a particle and an antiparticle shouldn't have any color. But they do, because you could have a red particle and a blue antiparticle. A red, that would make a thing which was not really neutral, which knew about color. So gluons do have color, and they have color in what is called the adjoint representation, which is the representation of the 8 generators. Okay, now, what about the interaction between quarks? Incidentally, there are many other gauge theories of interest. They're all pretty similar to each other. The group might not be SU3, it might be SU2, it might be SU4, it might be SU10, it might be anything. And the objects of the group might not be called quarks. Nevertheless, or the fundamental objects of the group, the analogs of quarks, might be called something else. They might have a different name. But they would be objects which had a single index. The anti-objects would also have a single index, but of the complex conjugate kind. And the analog of the gluons, which are called gauge bosons. Gauge bosons, the Maxwell-like fields, always have one index of the particle type and another index of the antiparticle type. So that means, let's see, if we're talking about SUN, that means how many generators altogether? Well, n times n is n squared minus 1 for the trace. So it's n squared minus 1 distinct gluons. Now, what is the connection between the quarks, or more generally, the particles which transform like quarks, perhaps in a more general way? What's the connection between them and the gauge bosons? And I've explained that to you before, but let me just remind you again. If you have a quark labeled by I, where I could be red, green, or blue, and another quark labeled by J, that the ith quark can become the jth quark if a gauge boson is emitted. What kind of gauge boson? Well, as I showed you before, the way to think about it is just to think about these lines running through the diagram. I runs right through, so that's I, and J also runs right through, except when J is pointing downward, it should be thought of as the analog of an antiparticle. And so an I would become a J by emitting a quantum of the field A, is it Ji or Ij? I think Ij. No, Ji. Doesn't matter very much. By emitting a gluon of the ijth type, an ith particle becomes a jth particle. And that is one of the basic interactions of gauge theories in general. Fundamental objects analogous to quarks, gauge bosons analogous to gluons, and a rule about emission and absorption that you have to follow the lines and never lose an index. But now that raises something new. If a gluon itself has the properties of a quark and an antiquark, so let's say this is the ijth kind of gluon. Well, the ijth kind of gluon can also emit a gluon. How would it do it? The ijth gluon could become the ikth gluon. Ij, let's say red-green gluon, could become the red-blue gluon as long as the indices make sense and they're followed, anti-K here. All right, so this would be an interaction in which a gluon of type Ij became a gluon of type Ik and a gluon of type Kj. Gluon of type Kj. The order of I and K matters. A Kj is not the same as a Jk. But all right, that introduces something absolutely new which is not in electrodynamics. Namely, that the gluons themselves are charged particles and therefore exert forces on each other. They exert forces in a way that photons do not, exert forces on each other. The dynamics of gluons is much, much more complicated than the dynamics of photons. The last time what I told you was that one of the, and I'm not going to do the mathematics of this, it's not even fully understood even now, but the effect, one of the important effects is that if you have a source, a color, a bit of color, with field lines coming out of it, again, those field lines are not allowed to end, right? They're not allowed to end, but the effect, let's suppose, is that's a quark, is an antiquark over here. Field lines have to come into it, so the field lines have to be continuous and so forth. Let me not draw more than that. Now, the effect is that the field lines interact with each other in a way that they don't in electrodynamics. And the effect is very simple. The field lines get pulled into bundles which are called flux tubes, the result of which is that no matter how far apart you pull two quarks, they'll never escape from each other because the energy stored in this gooey piece of glue just increases linearly with the distance between them. All right, that's a summary of quantum chromodynamics, but it's also a summary of gauge theory. It's also a summary, very, very quick summary of gauge theory. Maxwell-like fields, sources, Gauss's law, making sure you have conservation, and symmetries. Symmetries having to do with the conservation laws, but more than that, the symmetries telling you how the particles interact with each other in terms of emission and absorption. There is one other thing in a gauge theory, and it's the coupling constant. The coupling constant is the analog of the charge of the electron. The charge of the electron, let's talk about what the charge of the electron means. It is, of course, the coefficient in a Feynman diagram when you emit a photon from a charged particle. The amplitude for that, the quantum mechanical amplitude for that, is the electric charge. But if you wanted to think about it operationally, you can imagine an electric charge slamming into what is it, the cathode or the anode? Cathode. The cathode of a cathode ray tube. When it slams into it, it gets accelerated. And the question is, what is the probability that an electron which is stopped suddenly emits a photon? Okay? And the answer is the square of the electric charge. The square, it's really the square of the electric charge. There's some pi's in it and h-bars and things, but basically the square of the electric charge in suitable units is the probability for emitting a photon. So that's what, in quantum mechanics and field theory, that is what the meaning of the electric charge is. It's a measure of the square of the electric charge is the probability. Why? Because probabilities are always squares of amplitudes. But that's the fundamental significance of the electric charge. And the electric charge is a dimensionless number. Just the probability that when you stop an electron, you emit a photon. Okay? So it's a dimensionless number. It's a small dimensionless number. And with appropriate sets of definitions, the square of the electric charge, really what tends to come into things is not quite the square of the electric charge. It's the square of the electric charge divided by some 4 pi. 4 pi's are always floating around in there. It's called the fine structure constant. And the fine structure constant, which is pretty much the probability of a photon emission, is a number of about 1%. It's close to being 1 over 137, a famous number, 1 over 137. The 137 has no particular significance. It's just numerically about what the fine structure constant is. And let's just call it 1%. It says there's a 1% probability of emitting a photon. So if you had a picture that when an electron hits a cathode ray tube, it sends out a spray of photons, that's not right. What is right is that if 137 photons hit the cathode ray tube, on the average, one of them will give off a photon. In that sense, electromagnetism is a weak force or a weak process. The probability of emission is weak. All right, that's the quick summary of gauge theory. What I wanted to do is give you very, very briefly a rundown on some numbers and orders of magnitude in various parts of particle and atomic physics, and then go on to the weak interactions. Now, the reason I'm giving you a rundown about numbers is to show you how different the weak interactions. Quantum chromodynamics is the theory of the strong interactions. The strong interactions was the word before quantum chromodynamics was invented for the interactions between subnuclear particles, between hadrons, between protons, neutrons, mesons, and all the things which are made of quarks and gluons. So it's the theory of strong interactions. And there are electromagnetic interactions, and there are also weak interactions. So I want to spend a little bit of time with numbers to show you where the terminology came from, why one is called weak, why one is called strong, why electromagnetism is sort of in the middle between the two of them. But let's just review a couple of numbers. First of all, in terms of units. Energy distance and time do not have to be thought of as different units. They're all related with each other. First of all, time and distance really should not be distinguished in any sensible set of units that are useful for fundamental physics. We can set the speed of light equal to 1, and if we fix the speed of light equal to 1, then time and distance have the same units, and we can use the same units. As far as energy goes, we could also choose to set Planck's constant equal to 1. That's a useful thing to do in quantum mechanics. An awful lot of equations get simpler if you set h bar equal to 1. Well, they don't get a lot simpler. It just gets rid of the h bars. But you can set h bar equal to 1. Now let me just remind you, there's a connection between energy E equals h frequency, right? Or h nu, or h bar omega, all the same thing. The units of h bar, well, we've set h bar equal to 1. So in units in which h bar are equal to 1, energy is equal to frequency. But what's the units of frequency? 1 over time, number of oscillations per second. So that means that energy and time have inverse units to each other. You don't need to have a separate unit for time and energy. Anytime you have a unit of energy, it defines also a unit of time. Now, of course, the unit of energy is inverse to the unit of time. So big energies correspond to small time intervals. Okay, so let's write down some connections. And since energy and time are connected to each other, and time and space have the same units when c is equal to 1, then time and space have units which are just inverse units to the units of energy. So for example, here's a unit of energy, 1 electron volt. We've used electron volts before. 1 electron volt cannot be thought of as a unit of distance, but the inverse, 1 inverse electron volt, in other words, 1 over an electron, 1 inverse electron volt is a unit of distance. And just to have an idea of what it is, it's about 10 to the minus 7th meters. 1 electron volt is about 10 to the minus 7th meters. So an electron volt is a fairly small distance, but on the scale of fundamental physics, it's not a small distance. 10 to the minus 7th meters is what? Atom is 10 to the minus 10th meters, something like that. Yeah, okay, so it's fairly big. An atomic diameter, yeah, and we can, right, and an atomic diameter, 1 atom, this is the atomic diameter, that's about 10 to the minus 10th meters. And so you can convert that to electron volts. How many electron volts is it? I don't know, whatever it is. An inverse of about 1,000 electron volts, a kiloelectron volt. An inverse kiloelectron volt is an atomic diameter. Okay, another fact, just converting distance. If we know the distance or size of an atom, then we know the time that it takes light to go across it. All right, so the transit time is another quantity. Transit time, the time that it takes transit time, the time for light to cross an atomic diameter. What is that? That's about 10 to the minus 18th seconds. I've used the fact that light goes at about 10 to the 8th meters per second. Order of magnitude 10 to the minus 18th seconds. These are just some numbers that I just wrote down. But a different time scale. All right, so this is the time scale for light to go across an atom. A different times, and by atom, I don't mean the nucleus, I mean the whole atom. Another time scale is the time scale that it takes for an electron to orbit an atom. Now you might think, why isn't that just about the transit time? Transit time is about 10 to the minus 18th centimeters. The reason is because electromagnetic forces are fairly weak. Because they are fairly weak, the force on, and the ultimate reason that they're weak is because this fine structure constant, this alpha, which is e squared over 4 pi, That's a small number of about 1 over 137. Another way to say it is the electromagnetic force on an electron is weak. Because of that, the acceleration on the electron is not too big, and the orbit is fairly large. The weaker the force on an object, the larger the orbit is going to be. The slower the electron will move is what I meant to say. The slower the electron will move, and because the electron moves slowly by comparison with the speed of light, how much slower? About 1% slower. About this much slower. The electron moves around with only about 1% the speed of light, and that means the orbital time, that's about 10 to the minus, let's see, it's bigger. That time is bigger, 10 to the minus 16th seconds. Another quantity sometimes of interest is the decay time for an atom. How long does it take for an atom, an excited atom, let's say a hydrogen atom with its electron one orbital up from the ground state, one orbit up from the ground state, how long does it take to decay? Now, that is small, doubly small, with 2 powers of alpha. What are the 2 powers of alpha? First of all, the acceleration of the electron is small. Remember, charges emit radiation when they're accelerated. The acceleration is small because the force is small. So first of all, the acceleration is small. The electron moves around with a relatively small acceleration compared to what it could have been if alpha were bigger. It moves around with a small acceleration, but on top of that, just like the electron plowing into the cathode ray tube, there's another factor of alpha when the electron is accelerated in the probability that it emits a photon. So as the electron goes around here, first of all, it's moving with a slow acceleration, and second of all, even that acceleration is not very efficient in producing photons, just because the fine structure constant is small. The net result is that the time scale, order of magnitude, decay time, how long it takes for an atom to decay time is about a nanosecond, 10 to the minus 9 seconds, much longer than the orbital time or the transit time. So the main thing is there's a variety of different scales in the atom, and they're all related by the fine structure constant. They're related by powers of the fine structure constant. The fine structure constant being a small number, there are fairly large ratios between different time scales, transit, orbital, and decay time. All right, now let's come to hadrons. Hadrons are like atoms. They're atoms made up out of quarks. We could ask very much the same kind of questions. First of all, we could ask, what is the hadronic diameter? The hadronic diameter of a typical hadron, it could be a proton, neutron, meson, they're all more or less the same. Here's hadrons. Hadrons. The hadronic diameter is a lot smaller than the than the atom. It's a lot smaller than the atom. It's not 10 to the minus 10th meters. It's about 5 orders of magnitude smaller. (10 to the minus 15th centimeters). That's also more or less the diameter of a nucleus. Nucleus, of course, being a few protons and neutrons, is going to be bigger. Meters. Hadron diameter is about 10 to the minus 15th meters, 5 orders of magnitude smaller than an atom. Part of the reason is because, there's 2 reasons. There's 2 reasons why it's small. One of them has to do with the fact that the constituents are heavier, and heavier things will sit closer to the center. The other has to do with something else that we'll come to in a minute, but it's about 5 orders of magnitude smaller. The transit time is just gotten from the size straightforwardly. Transit time, this is not an independent thing. It's just another measure of the size of the thing. just to get the numbers straight, it's 10 to the minus 23rd seconds. So that's a typical time scale for, well, it's for light to cross the hadron. Okay? But now we can also talk about the orbital motion of quarks. How long does it take for a quark to swing around its wave function or swing around the interior of a proton? And there, the answer is about 10 to the minus 23rd seconds. What about the decay time of a typical hadron, in a typical excited state of a hadron? A vibrating hadron or an oscillating hadron, how long does it take for it to decay? And the answer is about, now I'm talking about particular kinds of decays. A decay where you hit a proton, it starts oscillating, and then emits a pion. Right? Those decays have a lifetime of about 10 to the minus 23rd seconds. Different than this hierarchy of scales here. What is the conclusion? The conclusion is the analog of the fine structure constant is much bigger, close to 1 for hadrons. In other words, the emission probability, if a quark were to get stopped in a fictitious cathode ray, quirky cathode ray tube of quark flying off, the probability for it to emit a gluon would be about 1. Right? That's what these things indicate here. The hierarchy here is entirely due to the fine structure constant. The lack of a hierarchy here can only mean that the corresponding quantity in quantum chromodynamics must be close to 1. By now it's been measured in many ways, and it is much closer to 1. It's much larger than the corresponding quantity for electrodynamics. 1 is a little bit, no.
It would seem that just special relativity would say that the decay time shouldn't be much less than 10 to the minus 23, because that's the time it takes light to go from one.
Yeah, I think that's a fair statement. Yeah.
So
It's about as fast as it could be, in other words. It's about as fast as it could be. Nothing slowing it down. Huh? This is why the strong interactions are called strong. Now, the facts about the numbers here were known before quantum chromodynamics, and it was understood that there was no hierarchy of scales, and that's why it was called strong interactions. We now trace it to the properties of the charge or the fine structure constant. Incidentally, for quantum chromodynamics, the analogous quantity is not really 1, it's about a fifth, but much bigger than the 1 over 137 here. All right, so that was just some numbers and some facts about.
So this one is the fine structure constant, and then the other is called what? The strong force constant.
It's called alpha QCD. Right. So this is called alpha, and the other one is called alpha QCD. And it's about 0.23 or something like that.
Or in context, the paper may write alpha QED.
What's that?
In context, the paper may write alpha QED.
I've never heard alpha QED referred to as alpha QED, but I think if you were writing a paper with both of them, you might call the top one alpha QED, yes. I've never seen it referred to that way.
Well, particularly if you're talking about shielding or something like that.
No, I don't think I've ever seen it. But oh. It's just called alpha. Sometimes the unshielded one is called the bare alpha. The shielded one is called the renormalized alpha. Right. Okay. Well, that brings us to the weak interactions. The weak interactions are called weak primarily because the decay times associated with them are very long. They're much longer than the decay times associated with either hadrons, and they even tend to be longer than the decay times associated with atoms. So there are processes in nature, decay processes in nature, in which particles, elementary or otherwise, decay by weak interactions where the time scale, in other words, the half-life for these decays, is far longer than any scale that can be accounted for by these by numbers like this. So as an example, here's some examples. Well, the lifetime of the neutron. The neutron is a hadron, and it decays. Neutron goes to electron, proton, plus antineutrino. And the lifetime for that is about 12 minutes. That's absurdly long on particle physics scales. Part of the reason is easy, but it hardly accounts for the extraordinary stability of the neutron. Part of the reason is the neutron is only a little bit bigger than the combined masses of the electron, the proton, and the neutrino. Let's just see. Somebody have out their pocket the mass of the neutron is 940 MeV. I don't know, 940, about 940. The mass of the proton is about 939. I think the actual difference between them is about 1.5 MeV. But then there's the electron, which has a mass of about half an MeV. Altogether, out of this 940, almost 1,000 MeV, the difference of mass of the proton, the amount of available mass left over is tiny. It's 0.1% or less. If the neutron was slightly lighter than the sum of these masses, it could not decay at all. Just energy conservation would not allow it. Remember, mass is energy. It would not have enough energy to decay and still leave over some energy for kinetic energy of these particles. So if the neutron was exactly the same as the sum of the energy of the electron, the proton, and the neutrino, the sum of the mass of them, it wouldn't be able to decay at all. If you gave it a mass tiny, 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 tiny bit above that, it would be able to decay, but it would take a very long time. The decay would be very slow. So part of the slowness or the long lifetime of the neutron is attributable to the fact that there's very little energy available for the decay to take place. But given that, that's hardly the bulk of the story. 12 minutes is so absurdly long that there's something much, much more than that going on. Another example, let's see, where do I have it? I guess I didn't write it down. Another example of this is called a weak decay. For obvious reasons, it's called a weak decay. Another example is a charged pion. Let's say a pi minus. A charged pion decays to an electron. Electron has negative charge, and an antineutrino. Yes, and an antineutrino. That's another possible decay. Charged pion goes to an electron and an antineutrino. A positively charged pion could become a positron and a neutrino. The lifetime for that, I believe, is about 10 nanoseconds. Longer than these atomic decay times, and atomic decay times are very, very long by comparison with particle physics decay times. Now, this there is a decay of the charged pions to these particles. There's another decay involving muons. We're going to come to muons soon enough, similar to electrons. But the point is not the particles that they decay into, but two things. First of all, they also decay very slowly, nanoseconds. But there's plenty of energy available for these decays. These decays are not suppressed by the fact that the energies of the initial or the masses of the initial and final states are very close to each other. So there's something else going on in weak interactions. Whatever weak interactions are, there's something that makes them proceed very, very slowly and weakly. All right, so that's what we come to next, is weak interactions. The primary or oldest example of which is the decay of the neutron, the beta decay of the neutron, called beta because electrons were originally called beta waves. All right, and this is called the beta decay of the pion. And in fact, it's quite similar physics goes into both of them. So to understand what's going on, we need to understand about some more particles. Particles that we haven't come to yet, the leptons. Let's go back to the quarks for a moment, and let me just make a table of the different kinds of quarks. Horizontally, or make a sequence here, which will be red, blue, and green. These are the colors of quarks. And then along here, let me list the up quark, the down quark, the charmed quark, the strange quark, the top quark, and the bottom quark. Each one of these boxes is filled. There are red, blue, and green up quarks. Let's put an X there. There's an X here. There's an X here. There's an X here, X here, X here, and so forth. These X's represent all the possible quarks that exist. Now, quantum chromodynamics has to do with symmetries which connect red to green to blue. It has to do with these unitary transformations which mix up the colors of quarks. They do not, those symmetries do not mix horizontally. An SU3 symmetry, a color symmetry, may rotate an up red quark into an up blue quark or an up green quark, and the nature of the symmetry is to act vertically, to mix up things this way. It also, at the same time, will mix the different down quarks, the different colors of down quarks. The same symmetry will mix the different colors of charmed quarks and strange quarks and so forth. So the color symmetry acts vertically. It mixes up the different rows here.
So is that unitary matrix?
Yes, the unitary matrices mix up red, green, and blue. I might have done better to put the rows where the columns are and the columns where the rows are, but no, it's okay. It's good. It's good. No, it's good. It's good. Right. The weak interactions are associated with symmetries which act horizontally in this picture. They mix up with down. They mix, in the same time that they mix up with down, they mix charm with strange. And they mix top with bottom. Let me just remind you that an up quark has the same properties, apart from its mass, same properties as a charm quark or a top quark. The down quarks are similar to strange quarks and bottom quarks. Ups have charge 2/3, downs have charge minus 2/3. Same here and here. All right? So these are symmetries which mix, if you like, upness with downness. At the same time, charmness with strangeness and topness with bottomness. Mixes these up. the symmetries. Those symmetries, what would you care to speculate on what group might be involved? SU2, because it acts on things, on doublets. We simply have three doublets here. They don't take up to charm or up to top. They simply act on up and down, horizontally, among pairs of things. A group SU2, and it is a gauge symmetry. In other words, it is also comes together with forces, with gauge bosons, with interactions, and with gauge interactions, with gauge fields. We're going to get to those short enough, but we've left out something from this table here. It's kind of as if there was a fourth color. Now the reason, the fourth row here is not usually identified as a color, and the reason is because the particles do not interact with the gluons. But nevertheless, it is another row here, another row in which there are particles which are filled in here, and in a certain sense, or not in a certain sense, they are also doublets. These particles are also doublets and also get mixed up under this SU2 symmetry, which moves things horizontally. Right? What are they? What are those particles? They're the leptons. So in a sense, the fourth color could be thought of as lepton number. But what are the leptons? The leptons are, first of all, in the first column here, there are analogous to the up or analogous to the down, there is the electron. The electron is a lepton. But its partner is the neutrino. But there are different neutrinos. There's not only one neutrino. This is called the electron neutrino. What comes in the next column? The muon. The muon, in every respect except for mass, is the same as an electron, just as in every respect except for mass, the charmed quark is like an up quark, or the strange quark is like a down quark. And together with it, there's its own neutrino, the muon neutrino. And finally, the last one is called the tau, and nu sub tau. All of the charged leptons, incidentally, neutrinos, of course, as you might guess from their name, are electrically neutral. The electrons, muons, and taus have charge -1. Okay? They are put under the down column here, not because their charge is the same as the down charge, but because the difference between the charges of the two is the same as the difference up here. What's the difference between the charge of an up and a down? 2/3 minus 1/3. So the difference between this column and this column is plus 1 unit of charge. The difference between this column and this column is also 1 unit of charge. 0 minus -1. So as you go from here to here, you decrease charge by 1 unit as you go horizontally. Now, should we take a break for 5 minutes? Let's take a break for 5 minutes. And then I will tell you about the W bosons. W bosons are the gauge bosons of the weak interactions. All right, so let's try now to see if we can make a microscopic gauge theory of the weak interactions. As I said, the weak interactions are based on a gauge theory which mixes up to down, neutrino to electron, and so forth. And so rather than to get into mathematics for the moment, the mathematics of the group SU2, which we'll come back to, let's think a little more simply. We've seen that in various situations, the gauge bosons typically have the quantum numbers or the quantum properties of a particle and an antiparticle. In the case of the In the case of the quantum chromodynamical interactions, it is a quark and an antiquark, so that's why we had 9 gauge bosons and so forth, or 8 removing the trace. So we could start by saying, let's look at the possibilities of gauge bosons which have the properties of of a particle and an antiparticle. But let's not distinguish between whether we're talking about quarks, red quarks, blue quarks, green quarks, or leptons. Let's just say a particle from this column with an antiparticle of this column. And for simplicity, let's just focus on the leptons. You'll see in a moment that you'll get the same thing if you focused on the quarks. But let's focus on the leptons and talk about objects that we could make with a lepton and an antilepton. All right, first of all, we could have some simple things, electron with a positron. Now, I don't really literally mean electrons and positrons. Okay? We could have electrons and positrons. Electrons and positrons have no charge at all. So let's drop that for a minute. We'll come back to it. There are things which have properties of electrons and anti-electrons, neutrinos and antineutrinos. But more interesting for the moment is the combination of electron antineutrino. So what is the charge of an object which has the same conserved quantities, the same properties as an electron with stuck on top of an antineutrino? Well, let's just focus on its charge, its electric charge. Its electric charge is -1. Neutrino is neutral, electron has negative charge. So whatever this object is, it has negative electric charge. Let's give it a name and let's call it a gauge boson. Let's assume that it is also a gauge boson. Gauge boson means that it behaves like the Maxwell field, the whole same thing, but it has negative charge. Let's call it W. W, that's the traditional name for it. W minus. Why minus? Because it has negative electric charge. We could, that was this one with this one. We could have taken down quark with, I guess, anti-up quark. Yeah, down quark. What happens if you take down quark with anti-up quark? How much charge do you get? Again, minus. Same as this. Down quark with anti-up quark would also have minus charge. So, if you like, you could also imagine that the W minus has the same properties as a down quark and an anti-up quark. In other words, it's 1 from the second column and an anti-1 from the first column. That's the property that it has. Let's call it W for weak, in fact. I think W was originally the notation for weak. The negatively charged W boson. Okay. And of course, there's also a positively charged boson, W boson, which is like anti-down with an up, or like positron, E plus, with a neutrino. E plus with a neutrino would be a W plus. Let's suppose the pattern is pretty similar to quantum chromodynamics, that the W bosons are like either photons on the one hand or like gluons, which means that they would be objects which could be emitted from the leptons. They would be objects which would allow a lepton of one kind, let me not label it, a lepton of one kind to become a lepton of another kind by emitting a W boson. Let's see if we can find some examples. An electron can emit a W minus to become a neutrino. Electron becomes neutrino by emission of a W minus. you see the action of the gauge bosons is to do the same kind of transition that the symmetry is ultimately going to be imagined to do, to mix electron into neutrino in very much the same way that the colors got mixed by emitting gluons. You could follow the lines if you like and say the electron and the antineutrino over here can be imagined to be a W minus boson. Same pattern. Let's just draw it by saying a W minus is emitted. But that's not all you can do with the W minus. You can also have a down quark go to an up quark. With a W minus. That also works. And in fact, the W minus is an object which can be emitted in a transition from, let's see, from the right column to the left column. A red down quark can become a red up quark by emitting a W. A blue down quark can become a blue up quark by emitting a W. Likewise for green. But you can go further. The strange quark, not the strange quark, the strange quark can become a charmed quark. That's another one. Strange quark, charmed quark, again, W minus. So this new symmetry, this idea of a new symmetry which acts horizontally and only horizontally between neighboring pairs here, introduces the possibility of gauge bosons which cause transitions between electron neutrino, down quark and up quark, strange quark and charmed quark. Now a W plus and a W minus are antiparticles of each other. The meaning of that is that you can flip these diagrams, put the W minus down, W here, but when you flip it, it becomes a W plus. So a W plus can be absorbed by an electron, plus a unit of charge, minus a unit of charge to become a neutrino. So a whole family of different processes are codified by this one vertex here. We can turn them upside down. Neutrino goes to, you know what we're allowed to do. We've done these things before. And that's the basic new element of the weak interactions. Actually, that's all, yeah.
Well, it's not clear to me why you have W minuses in all three of these cases.
It's electric charge conservation. It couldn't be W plus.
Well, yeah, except I don't know what a W means.
W is the name of a particle. It's the name of another gauge boson.
Yeah, but the charge conservation tells me it's going to be a minus.
Right.
But well, I haven't seen any reason why it should be the same particle for the two.
Well, okay, that's right. But what it comes down to in the end is an empirical fact. It's the empirical fact that the symmetry of the weak interactions acts simultaneously on all of these doublets here. When an up goes to a down, a charm has to go to a strange, a tau has to go to a top has to go to a bottom, and the leptons have to mix with each other simultaneously. The implication of that from a practical point of view is simply it's the same symmetry which acts, it's the same gauge bosons which are there. You could have imagined a theory in which it's quite mathematically consistent to imagine a theory where different W-type bosons would have been emitted by up quarks, charmed quarks, or tau quarks, or even leptons. Right? It's a fact of nature. A fact of nature that nature is simpler than it might have been, that the same gauge bosons cause transitions between any row, any point row, you know what I mean. I'm going to get tongue-tied if I try to say it. Okay, well, first of all, what processes can we explain? First, yeah.
Quick question. Can a W minus decay into an electron and a negative neutrino as well?
A negative, say it again.
Can you flip the arrow?
Yes, 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 yes. You can flip arrows and you can flip lines. Yes, yes, certainly you can flip arrows. Yeah, absolutely. Absolutely. And you can also flip lines up and down in various ways. For example, another way you could flip the line is you could take this up quark here, have it, instead of going out, instead of an up quark going out, an anti-up quark comes in. Whenever you flip a line from past to future or from future to past, you'll also change from particle to antiparticle. Yeah.
I'm not understanding this. On the right post diagram, W minus there is a strange anti-charm.
Yes.
So that's the same as a down anti-up?
Yes.
Look the same?
Wait, sorry. Yes.
That's a strange anti-charm, right?
Yes.
That's the same as a down?
It's not literally a strange and an anti-charm. It's just a rule that tells you that whatever these W bosons are, they're associated with transitions from one column to the other. Did I? Sorry, strange. Wait. Electron to neutrino, strange to charm. Is that wrong? No.
It's not an anti-charm, that's the point.
Who said it was an anti-charm? No. No, no. All right. If you follow the lines like that, at the point where the line turns around, it has to be thought of as an antiparticle. Right? Okay? Or if you like, you can always think of it as strange anti-charm coming in and making a W boson. Okay? Just keep in mind, whenever you flip from the past to the future, if you want to know what a W boson will decay to, let's read it downward. It will decay to a strange and an anti-charm. All right, and that really can happen, yeah.
So can you create a W boson from like electron and a
Anti-neutrino.
anti-neutrino,
Yes.
and then cause the W boson to change into like a strange and a charm?
Exactly. That's where some of these processes are going to come from now. So let's think about the various processes. Let's start, just for fun, let's start with the decay of the pi minus. What is a pi minus? A pi minus is a quark and an antiquark with altogether negative charge. So let's see, a quark and an antiquark with negative charge had better be, here's the pi minus, that's equal to a down quark and an anti-up quark. Down and anti-up. Now, what can a down and an anti-up do? Let's see if we can find down and anti-up here. Here it is right here. Down and anti-up can become a W minus. That's a possible transition that is allowed by the physics of W bosons. So here's a W minus. But now a W minus can do something else. A W minus here is, let's see, here is W plus. Let's put W plus upstairs here. Sorry, this is W minus now, and let's put the neutrino downstairs, anti-neutrino, and read this as saying that W minus goes to what? Electron, anti-neutrino. So W minus can go to electron, anti-neutrino. And here it is. E minus, ordinary electron. So that's the basic underlying process that governs the beta decay of the negatively charged pion into a electron and an antineutrino. Now, which antineutrino is it? There are three distinct antineutrinos. It's the electron antineutrino over here. So it's the electron antineutrino. But it can also, I didn't draw all the various possibilities, but any place you saw an electron, you can put a muon. Any place, and as long as you carry along the muon neutrino. So another process is muon, anti-muon neutrino.
And just for clarity, this is not strictly a Feynman diagram, right? This is just showing an interaction.
It's pretty close to a Feynman
Well,
diagram.
except for the time direction.
Yeah, right. Turn it off. I don't know why all of a sudden I changed directions. Yeah, for some reason. Yeah, right. Time is now going horizontally. I've become a computer scientist, and they measure that. Yeah, they do. Right. Yeah, it's pretty much. Yeah, it's good. We turn it up. I can't do that easily, but yeah. Yeah, that is essentially a Feynman diagram describing the decay of the pi minus to the muon. As it happens, for technical reasons having to do with some complications in Feynman diagrams that are not interesting to us, as it happens, the primary decay, well, primary I mean the most probable decay of the pi minus is to the muon antineutrino, not to the electron antineutrino. It's a technical point of no special interest to us. It just happens to be that way.
Wouldn't it be consistent, instead of considering these Feynman diagrams with the time deal, is more like a chemical equilibrium deal, which way you're going?
Well, both things can happen. Both things can happen. It's not this. We're not in chemical equilibrium. We're in empty space. We're in empty space, except somebody made a pi minus. A pi minus was created how? A pi minus might be created by some nucleons coming together and creating by strong interactions. By strong interactions, a pi minus might be created. Now that pi minus is just going along and saying, wait a minute, I can decay, if I like, into a neutrino and a muon. Then, of course, the neutrino and the muon have enough energy, kinetic energy, to fly off, and they won't come back together again because they've departed, they've gone away. Okay, on the other hand, it is true that if you were to take a muon and an antineutrino and fire them toward each other, there would be a certain probability that they would make a pi minus. So, yes, you can read it both ways. Let's go, yeah.
Quick question, you have, like in one dimension, you have a SU3, the other an SU2. Is it possible to like combine them into an SU6 or something?
SU5.
Oh, well, not greater.
SU5, SU5. Not 2 times 3, 2 plus 3. Yeah. Right. Right, SU5. But not tonight. Tonight we want to get to SU2. I'll be happy if we get the basic ideas of SU2. All right. Now, keep in mind, we're doing something a little bit funny because we have, SU2 has how many generators? 3. So how many gauge bosons should it have? 3. So far we only have W plus and W minus. There must be another one lurking around, and that other one must be associated somehow with something like electron, anti-electron, and neutrino, anti-neutrino, but we'll come to it. Just like the, yeah, we'll come to it. There is a third gauge boson lurking around, and it does play a big role in the weak interactions, but it didn't play a big role historically in the weak interactions just because, for reasons we'll come to. Historically, it was the W boson, which was the first to be conjectured. Yeah.
Well, speaking of historically, was the weak or the strong force sort of suspected first?
Of course. All right, so let's talk about the history. The history of these forces goes back to Becquerel, goes back to radioactivity. Alpha, beta, and gamma decay. Alpha decay was what? Emission of 2 protons and 2 neutrons from a nucleus. That's a strong interaction. It's part of the theory of hadrons and nuclei. Beta decay, that was this one right here. weak interactions. And gamma decay, photon. So historically, they happened at the same time in the same experiment.
Question? The energy conservation, how it works there? You're assuming some kinetic energy involved in this?
Okay. Yeah, the energy. All right, let's work on that. You never worry about the energy conservation in intermediate states like this. If the energy of the intermediate state doesn't match the energies of the initial and final state, it just means that the intermediate state can only last for a very short time. There's an energy time uncertainty principle. You can violate the energies in a Feynman diagram for short periods of time. So don't worry about conservation of energy between here and here. The only energy we have to worry about is the initial energy and the final energy. Okay, so let's worry about it. A pion has an energy of about a mass. Let's suppose the pion is at rest. The mass of the pion is roughly about 140 MeV. All right, what is the energy of the muon and the neutrino? Well, first of all, it's the rest energy of the muon and the neutrino. Okay, and the rest energy, the rest mass of the mass of the neutrino, sorry, the mass of the muon, I think is about 100 MeV. I forget exactly. And the mass of a neutrino is, for practical purposes, 0. Too small to be important here. Right? So there's more energy to start with than the energy in the masses of the two final particles. Does that mean it can't happen? No. It just means the two particles will go off and carry some kinetic energy. So the difference between the energy on this side and the sums of the masses on this side is just the kinetic energy of the outgoing particles. That's the energy balance. The momentum also has to be conserved, and that means if the pion was at rest to begin with, the momentum of the muon and the momentum of the neutrino have to be equal and opposite, and they'll go out back to back, so to speak.
If you analyze the neutron decay in the same way as you looked at...
We're going to do that now. Yeah, let's do the neutron decay right now. See how neutron works. Oh, let's do something simpler first. Let's do the muon decay. The muon is also something that can decay. So let's take the muon. Here's the muon moving along. Now what can the muon do? The muon can become a neutrino submuon and emit a W. What kind of W? W minus, right? It can become a W minus and a neutrino. Okay. But now, one of the things that W minus can do is it can become an electron and an antineutrino. So this W minus can now become an electron and an antineutrino of the electron variety. Can this happen? The only thing that would, yes, it can happen. Not only can happen, this is the way the muon decays. The muon decays because it is sufficiently much heavier than the electron, much heavier than the electron, about 200 times heavier than the electron. The neutrinos are practically massless, so the energy balance is you have about 100 MeV here, a half an MeV here, and the rest goes off in kinetic energy. So that's an example of a what's called a purely leptonic process. No quarks in it at all.
Is it an antineutrino?
Is it what?
An anti-electron.
Yeah, it is. Right. So it's one neutrino, one antineutrino, and an electron. Okay, so that happens, and that's the primary decay. It's the only decay of the muon. So the muon is an unstable particle because of this, but the reason the muon is unstable and not the electron is just that the muon happens to be heavy enough to be able to decay to the electron. The electron is not heavy enough to decay to the muon. So in a sense, it's an accident of the masses. The same is true of the tau, incidentally. The tau can also decay to other leptons. But, all right, that's the mu decay. And notice the components are the same. The basic components are the same. A transition from one column to another, followed by a W, and then the W makes another transition from one column to the other, or, if you like, a decay from one column to the other. All right, what about the decay of the neutron? Decay of the neutron.
Would it be consistent to say the purpose of a linear accelerator, per se, is to effectively increase the mass of the electron so that it can now go the other direction?
Absolutely.
Yeah.
Yeah. Yeah. Yeah.
I mean, you don't change the mass, you just put enough energy
You
in
put
it.
enough, absolutely. Yeah, that's exactly right. Okay, we were going to do neutron decay. So the neutron is, maybe I better switch to vertical. I don't want to. All right, vertical notation, back to vertical. Neutron is 3 quarks, 2 down quarks, and an up quark, right? Minus 4/3 plus 2/3, sorry, minus 2/3, yes, that's a neutron, electrically neutral. Neutron coming in. Okay, now what is possible? First of all, we can have the up quark become a down quark and emit some sort of W, but that'll give us 3 down quarks. 3 down quarks is a fine thing. There's nothing wrong with 3 down quarks, except that the mass of 3 down quarks, of a particle with 3 down quarks, is always too heavy for the neutron to decay. So that's not what happens. What about one of the down quarks? The down quark can emit a W, become an up quark. This is again a W minus. The down quark emits a W minus, becomes an up quark, and now we have 2 up quarks and a down quark. Up, up, down. What is that called? Proton. That's a proton. And the W does what the W always does. It decays to an electron and an antineutrino. Electron, antineutrino. So that's the beta decay of the neutron. Could it decay into a muon and a neutrino? Not enough energy. The muon is too heavy so that there wouldn't be enough energy left over for the muon. But other than that, if it were not for that, it could happen. Another way to say it is if you could jam some more energy into the neutron. How can you do it? You hit it. You give it a shove. You give the neutron a whack, you excite it, and if you excite it enough, it can decay to a proton, a neutrino, antineutrino, and a muon. But without somehow providing that extra energy, the neutron will only decay to the proton, electron, and antineutrino. Okay, now let's see, where are we? I think we're finished for tonight. But remember, we have a puzzle. And the puzzle is, why is it that the weak interactions give such slow decay rates? And I can think of one reason, namely the coupling constant, or the analog of the fine structure constant, could be ridiculously small, so that the probability of emitting these W bosons would be very, very small. That is not the reason. The fine structure constant for the weak interactions is about the same as for electromagnetism. That is not the reason. The reason is something else, and we'll come to the something else next time. Yeah.
When you say the theory has these symmetries, you mean that the Lagrangian is the field?
The Lagrangian is invariant under those operations. That's exactly what it means. I didn't want to start writing bunches of Lagrangians, so I've used the shorthand of saying there's a symmetry, right? But that's what it means, yeah.
For more, please visit us at stanford.edu.